welcome to week 5. In this week, we shall be discussing on memory system design. So, we will look into the various technologies that are used to build the memory that we use in computer, and we will also look into how these memory are used to design and organize it in the system. So, memory is one of the most important functional unit of a computer. We all know that. What it is used to store both instructions and data, and it stores bits like zeros and ones. So, as we have already seen how we encode an instruction with bits of zeros and ones. So, in the memory location, when we say we store both instructions and data, those instructions and data are organized in bits of zeros and ones, and they are usually organized in terms of bytes. So, we will see here how are the data stored in the memory are accessed. So, like in memory, what we are saying, we store data. So, we need to know the mechanism how we can access the data from the memory. We should also know how we need to store the data into the memory. So, these are the two things we need to look into. Every memory location has a unique address, and a memory is byte addressable, that is every byte, that is a group of 8 bits, has a unique address. Some memory systems are word addressable, and by word addressable we mean that each location consists of multiple of bytes depending on the word size. If your word is, one word is 4 bytes, that is 32 bits, then the memory location will be changed after every 4, 0, 4, 8 and so on. And if the every address location consists of like multiple bytes, so if it consists of 8 bytes, that is 64 bits, then the word length is 64, then the memory system, in the memory system it will be incremented by 8. Now, see the connection between processor and memory. So, as you know that in processor we have two important register, one is memory address register, another is memory data register. Memory address register contains the address of an instruction or data that is to be read from the memory, or the address of a data that is to be written into the memory, and that particular data which is to be read comes through this data bus. So, this is the data bus, and whatever address is here, that address is hit, and then from that address whatever data is present, that data comes through this data bus and it comes to memory data register. Now, you see that the data bus is bidirectional, because we can read the data from the memory. So, the data is coming from the memory to MDR, and for write we have to write the data. So, from MDR it will go through this data bus into memory, and along with this we also require some control signals like read, write, etc. So, if we have a n bit address bus, then the memory addressable memory location will be 2 to the power n. Like we already discussed, if we have a 3 bit address bus, then the total number of location will be 2 to the power n. So, there will be 8 location starting from 000, 001, we go on with 111. So, n bit address bus can have a maximum of 2 to the power n addressable memory location, and we can have a m bit data bus. So, in that particular address, the data which is present is m bit, and m bit data at a time can be transferred to memory. And we have other signals like read write and chip select. We will be seeing that why chip select is required in course of time. So, this the maximum number of memory location that can be accessed is 2 to the power n. M bit data line, the number of bits stored in every addressable location is m, and the read write control signal selects the memory for reading or writing. So, for reading it is 1, for writing it is 0. As I said, chip select line, when it is active, that is it is active high, this is active low. So, it is active when it is 0. So, this will enable the chip when it is 0, otherwise the data bus is in high impedance state. So, this memory module will not be selected in that case. So, here we have n bit address bus. So, we have 2 to the power n addressable location and m bit data bus. So, the size of the memory, the total size of the memory which is addressable is 2 to the power n cross m. Now, classification of memory system. How we can classify a memory system? So, one way to classify memory system is volatile versus non-volatile. So, with respect to volatility, meaning a volatile memory system is one where the stored data is lost when the power is switched off. That means, as long as the power is applied to it, the data will remain, but as long as the power is taken off, the data goes off. That means, it is volatile, it goes off after the power is cut off. So, this CMOS static memory and CMOS dynamic memory, both these are volatile memories. That means, as long as power is supplied, the data remains, but in case of dynamic memory, even if we are supplying the power, then also it requires periodic refresh. So, data cannot be retained for longer period of time. So, periodic refresh is necessary. Now, what is a non-volatile memory? A non-volatile memory system is one where the stored data is retained even when the power is switched off. So, where you will see such kind of non-volatile memory? We see that in read-only memories, where once the data is there, it retains. Magnetic disk is also one, CD-ROM, DVD, flash memory and some resistive memories. So, here these are all non-volatile memories. So, even if the power is not supplied, the data will remain. Again, we can differentiate a memory with respect to random access versus direct or sequential access. What do we mean by random access? By random access, we mean that when the read or write time, the read and write time is independent of the memory location being accessed. That means, you either hit location 0 or you hit the last location or the middle location. The access time is same, random access. So, whichever location you access, the access time will be same irrespective of the location. The example is CMOS memory, that is RAM and ROM, both are random access. And then what is sequential access? A memory is said to be sequential access when the stored data can only be accessed sequentially in a particular order, like the examples are magnetic tape. Here the data are accessed sequentially. So, one by one by one. A memory is also said to be direct or semi-random access when a part of the access is sequential part and the part is random, like your magnetic disk. Here we can directly go to a particular track, but after reaching that particular track, if you have, we can sequentially get the data one by one by one. So, here this kind of memory is semi-random access. So, which is somewhat sequential, somewhat random. Next, let us see read only versus random access. What are read only memory? Read only memory is one where the data is once stored, is permanent or semi-permanent. What do you mean by permanent? What do you mean by semi-permanent? By permanent, we mean that once we write into it and then no changes can be made to it, that is permanent. And semi-permanent means we write into it, it remains, but if later we want to change it, we can still do it. So, it is semi-permanent, it remains permanent for a period of time, and again if you want to change it, we can change it and then it will again remain. So, the examples are ROM, random read only memory, PROM, programmable read only memory, erasable programmable read only memory, and electrically erasable programmable read only memory. So, these are all class of read only memory, where the data written or programmed during manufacturing process, when they are manufactured, at that particular time the data is written into it, but yeah, there it can be changed with progress. So, ROM came first, then PROM, then EPROM and so on. Now, random access memory is one where the data access time is same independent of the location. So, we access the first location or the last location, the access time will be same. And where it is used? We will be talking extensively about your main memory and your cache memory. So, in both the memories, such kind of memory, that is random access memory, are used. Some of the examples are static RAM. Here, once the data is written, it retains as long as the power is supplied to it, and dynamic RAM is having the same feature of a RAM, but even if the power is supplied to it, it requires periodic refresh. So, periodic refresh is required even if the power is supplied to it, and here the data is stored as charge on tiny capacitor. We will be looking into more details of static RAM and dynamic RAM in course of time. Now, at this point of time, we need to know some of the terminologies that we will be using it very often. They are called access time of a memory, latency and bandwidth. So, what is memory access time? By memory access time, we mean that the time between initiation of an operation, what operation? Either it can be read or write, and the completion of that operation. Access time, how much time it is required to access the particular data, that is memory access time. Next is latency. Latency is the initial delay from the initiation of an operation to the time the first data is available. So, let me tell one thing at this point of time, that when we access a particular location in the memory, we do not just access or retrieve that particular data, we always transfer a block of data. That is why this latency is an important term, because latency will give the time required to access the first data, and then the subsequent data that are present can be accessed in a much faster rate. So, latency is the initial delay from the initiation of an operation to the time the first data is available. And what is bandwidth? Bandwidth is the maximum speed of data transfer in bytes per second. So, in modern memory organization, every read request reads a block of words into some high speed register first, that is the first word is available, and from where the data are supplied to the processor one by one. Okay. So, the total access time will be depending on not only a single word, but block transfer. So, subsequent words, how they are transferred. Now, this graph I have already shown you earlier while talking about evolution of computer system, but now let us see the design issue of memory system. So, this red line shows the growth of processor in course of time, and this green line shows the growth of memory technologies. Although you can see both are growing, but processor design is growing at a much higher pace, and memory speed, memory design, memory advancement is coming at a lower rate, but both are advancing. Technology is advancing in both processor design as well as memory, but this speed gap is steadily increasing. So, the most important issue is to bridge this processor memory gap that has been widening with every passing year. So, this gap that we can see here is actually increasing. So, see, this gap is increasing. So, the advancements in memory technologies are unable to cope with faster advancement in processor technology, but there are many techniques that are used to bridge this speed gap. So, at this point some important question arises: how to make a memory system work faster? It has a limitation, but how we can make it faster such that the processor and memory speed gap can be reduced? How to increase the data transfer rate between CPU and memory, the transfer of data, how it can be made faster, and how to address the ever increasing storage need of application. We need large memory as well. Not only we need faster, we also need larger memories, because we need there are various applications which requires larger memory space. So, we need to look into all the issues. First issue is how we can make this memory work faster, how we can have a larger memory, and by all these things how we can reduce the speed gap between processor speed and memory speed. So, some possible solutions are cache memory and virtual memory. What a cache memory does, we will be looking into detail of this in later weeks, but what it does is it increases the effective speed of memory system. And what virtual memory does? It increases the effective size of memory system. So, we will be looking into these in some detail in the later part of this week. So, very briefly, what is cache memory? It is a fast memory that sits between your CPU and main memory, and we can have many levels of cache memory. And why cache memory is in place? We will see this because of two properties of computer programs. What is that? One is that is called locality of reference basically. One is temporal locality of reference, other is spatial locality of reference. So, we will see this in detail later, but for now let us understand that cache memory is a memory which sits between CPU and your main memory, and there can be many level of caches, but the cache memory cannot be very large. It is much smaller compared to our main memory. So, frequently accessed data or instruction can only be brought here and executed. And what technology is used to build this cache memory? We use static RAM technology to build this cache memory. Moving on with virtual memory. Virtual memory is basically it's a concept that is used to give an illusion that we have a very large memory space at our disposal, but actually we have space equal to main memory, but it gives an illusion to the programmer that you have a larger space to execute. So, the technique used by operating system to provide an illusion of a very large memory to the processor. Program and data are actually stored on secondary memory that is much larger, and data and instruction are brought into main memory as and when it is needed. So, secondary memory is a concept where we say that we have a very large memory, but whenever we want to execute it, we need to bring those data or instruction into main memory and then it can be executed. Now, let us see how a memory chip looks like. So, this is on a PCB printed circuit board. So, these are memory, this is a separate memory modules that are placed, and these memory cells are organized in the form of array. So, these you can see this is 1, this is 1, this is 1, this may be a 4 GB memory and each having say 1 GB, 1 GB, 1 GB like that. So, present day VLSI technology allows one to pack billions of bits per chip. So, per chip billions of bits can be put in. A memory module used in computers typically contains several such chips. So, these chips are put into the slots, memory slots that are present in the PC. Now, let us see organization of cells in a 8x4 memory chip. So, this is a 8x4 memory chip. Let us see how it is organized. So, you have 8 rows. This is the first row, second row, third row, fourth row, and this is the 8th row. And in each row, there are 4 bits which can be taken out. An individual memory cell is a row. Let us consider this as a row. This row is connected with the word line. This is called word line, W0, W1, W2, these are word line. An individual cell is connected to 2 bit lines. One is B, another is B bar, that is complement of the other, and which is connected to the sense or write circuitry, and this sense or write circuitry is further connected to the data lines. That means, this is one memory chip where there are 8 rows. So, we have to select any one of the 8 rows. So, for that reason we require a 3x8 address decoder. So, these A0, A1 and A2 are applied to this address, and then depending on this particular address, let us say it is 000, then the first word line will get selected, and then all the bits of these word lines may be transferred through this sense or write circuit to the data lines if we want to read the data. And suppose I want to write the data into these cells, then what will happen? The data present in this data line, that is coming from your MDR, will get stored in this bits through this sense or write circuit. So, in this organization we can see that a 8 cross memory chip is there. So, the address is decoded with using a 3 cross 8 decoder, and then each of the bits, each of the memory cells are connected to 2 bit lines. One is the complement of the other, which is connected to the sensor write circuitry, and through the sensor write circuitry it is connected to the data lines. And we have to also supply these signals, that is either we want to read a data or we want to write a data. So, this is how the memory chip 8 cross 4 memory chip is organized. So, as I said, a 32 bit memory chip is organized as 8 cross 4 as shown in the previous figure. Each row of the cell array constitute a memory word. So, the entire row, entire one word is the row. So, every row of the cell will constitute a memory word. We need a 3 cross 8 decoder to access any one of the 8 rows, and the rows of the cells are connected to the word lines. Individual cells are connected to 2 bit lines, one is B, another is its complement, and it is required for reading and writing, and cells in each column are connected to sensor write circuitry. So, cells in each column, so this is one column, this is the next column, third column and fourth column. So, the cells in each column is connected to this sensor write circuitry. Other than the address and data lines, there are 2 control lines, read and write and chip select. And why chip select is required? It is required to select one chip in a multi-chip memory system. We will be seeing this with examples later. So, basically this read, write and chip select is connected such that either it will specify that you have to read the content of any one of the cell, one of the word, or you have to write data into one of these cells. Now, in this diagram, how many external connections are required? What do you mean by external connections? Externally, that is provided, not within this memory chip. You can clearly make out that these address lines A0, A1 and A2 are externally provided to this decoder, and then it is decoded and a particular word is selected. Now, once you select a particular row, then all these bits will be transferred to the data line through this sensor write circuit. So, it is connected to 4 bits are there. So, there will be 4 data lines through which this data will go. So, those are 4 more external signals that are required here. So, 3 for this address, 4 for the data lines, and then you have 2 more signal, that is read, write and chip select. That should be also provided externally, because the processor will tell either you have to read a data or you have to write a data. And there will be 2 more, that is power supply and ground. So, external connection requirements that are there for this 8 cross 4 memory, that is 3 external connection for address, 4 external connection for the data, because in each row there are 4 bit, 2 external connection, one is for read write and another is for chip select, 2 external connection for power supply and ground. So, a total of 3 plus 4 plus 2 plus 2, that is 11 is required for this 8 cross 4 memory chip. Now, let us see what about this 256 cross 16 memory. How many 256? So, there will be 256 rows. To select any one of the 256 rows, you require a 8 cross 256 decoder. So, the address decoder size will be 8 cross 256. So, 8 external connections for address will be required. then the data output is 16. So, 16 external connection will be required to transfer the data, either to read the data or to write the data. Similar way, 2 external connection for read, write and chip select, and 2 for power supply and ground. So, a total of 28 external connections will be required. So, we came to the end of this lecture, where we briefly discussed about what is memory, how a memory chip can be organized, and in the next few lectures we will be seeing what kind of memory technologies are actually used to build this.